Okay, so let's take a look at one of these. I want to go through real quick just a couple quick 3-4 problems where let's start off by graphing a function that's in general form. Okay, so in order to do this, right, we have to, it doesn't really work to just go directly from general form. We can't look at this and see, you know, where the vertex is and what the vertical dilation factor is all at once. We have to calculate h and k, right? So what is a, first of all?
3, negative 3.
Negative 3, okay, good. So then we want to find h and k. What's h, what's our formula for h?
2, or A, right? B, no, B over negative.
Negative b over 2a, good. So if we plug in, what's negative b? Positive 6 over 2 times a, what's a again?
Negative 3.
Negative 3, okay, so that's going to give us 6 over negative 6, which is negative 1, right? Okay, right back at you, Wyatt. So what's k going to be then?
K is going to be negative 1.
That's h. How do I find k?
You got to plug it in.
Plug it in. So k is going to be f of a, which is negative 1. So if I plug negative 1 in, let's see what we get. I get negative 3. I'm going to replace the x with a negative 1. So every place I have an x in my function, I'm going to trade it for a negative 1. And what's that give us? What's negative 1 squared?
1.
1 times negative 3, negative 3. Negative 6 times negative 1.
6.
Negative
6.
No, positive 6.
Oh,
Positive.
negative.
And then plus 3, so that just gives us 6, doesn't it?
Yep.
So our vertex then is going to be at
Well,
negative
1.
1, positive 6, right?
I did so much yesterday.
Good.
On my work days, I just freaking.
Good.
I got stuck, and I'll be honest, I didn't do that much.
Okay. Okay, so over here at negative 1, positive 6, there's going to be our vertex, right? Right there. Okay, if a is negative 3, let's look at some stuff here, right? So let's find some other points. So delta x, this is what we're going to call our horizontal distance from the vertex, is delta x. So if we go 1 to the right, what would our normal parent graph delta y be, vertical distance? Would be up 1, wouldn't it, right? So normally, so if we go 1 to the right, we would go up 1, right? What if we go 2 to the right? On our parent graph, where would we go? But what's our delta y? What's our vertical distance? This just stands for vertical distance. Delta y is
Oh, that's what I was wondering about.
vertical distance from the vertex. Delta just means change in, right? So for a change in x of 1, our change in y was 1. For a change in x of 2, our change in y should be what? 4. We're going to get 2 squared equals 4, right? Okay. For 3, what are we going to get? 9. Okay, we got the idea, right? Okay, what's a?
1, negative 1. What?
Negative 3. Okay, so it's negative 3, and that doesn't change. Right? A is
Bless you.
just, that's our a for this function. So if we want to find the dilated graph, all we have to do is just multiply the normal undilated y distance times a. That's it, right? So what's that give us? What is negative 3 times 1?
Negative 3.
What's negative 3 times 4?
Negative 12.
Negative 3 times 9.
Negative 27.
So those are the distances I would go from here. Right now, if we were to graph these points, wouldn't they just look like we're going to go over 1 and up 1? So we're going to have a point there. So we go over 2 on our parent graph, over 2, we'd go up 4. Over 3, we'd go up 9, so we clear up there somewhere, right? So there's our,
What are you multiplying times 3 to get those numbers?
I'm multiplying A times change in 1.
Oh.
I think you did your
Right.
parabola, isn't that what that thing's called?
Mm-hmm.
I think you did it wrong.
Oh, I did, whoops, you're right, I did. Huh, I did. Goes from there, doesn't it?
Yep. That one's better.
There we go. Like so. That's our parent graph, right? That's the red one. What's the blue one gonna be? Well, the blue one, we're gonna go over 1 and down
Down
3, right? So we're gonna go over 1 and down 3, so there's a point. We go over 2, and we're gonna go down 9,
Twelve.
so 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, sorry,
12.
12, whoops. So that's, I think, I can't even probably get to there. That's 1, 2, 3, 4, 5, 6, so it's way down, like, you know, way down there, right? So we can see that this guy is gonna be, he's gonna be tall and skinny, right? It's been stretched. Okay, does that make sense? How we're doing that, what that means? And so all we'd have to do is just go find the parabola that's got those values, where I go over 1 and down 3, over 2 and down 12, right? And really just use that one, that's all we need, okay? And it's got a vertex there, right? Okay, let's do one more of these. How about one like that?
Well.
So what's H? Or what's A, sorry?
1.
Negative 1.
Negative 1/2. Okay, let's find H and K. So H is, what's our formula again? Over, good. Okay, so then that's, what's negative B? So then 2 times A is 2 times negative 1/2. So what's 2 times negative 1/2?
Negative 1.
Oh, okay.
So H is negative 7, okay? Then K must just be F of negative 7, which is going to be negative 1/2 times X is negative 7, so I'll square that quantity, minus 7 times negative 7 minus 65/2. So what are we going to get? Negative 7 squared is what? Times negative 1/2?
Whatever's happening.
Yeah, negative 49/2 plus 49 minus 65/2, right? So all I'd have to do then, let's get a common denominator. I'd multiply this one by 2 over 2, wouldn't I? Right, so this is gonna equal
98.
negative 49/2 plus 98/2 minus 65/2. So what's that give us? If I add all those up, I'm gonna get negative 16/2,
Oh, that's what I was
which
gonna
is
say.
negative 8, okay? Okay, if we just simplify that. So our vertex then is gonna be at the point HK equals negative 7, negative 8, right? So that's where we're gonna anchor the curve. And then let's go ahead and look at what's gonna be our dilated values of delta y by comparing it to our parent graph, right? So let's look at horizontal distances of 1, 2, 3, and 4, how about, okay? So what's the parent graph value for a horizontal distance of 1,
1 squared.
which is 1, good.
4.
Oh, yeah.
4, good, you're right. 3 squared is 9, 4 squared is 16, right?
Right.
In this case, A is negative 1/2. And so if we multiply our parent, our undilated, our untweaked vertical distance by A, that's how we tweak it. What do we end up with? Negative 1/2 times 1 is,
0.5.
okay, negative, right?
Oh.
Negative 1/2 times 4.
2.
Negative.
Negative 2.
Negative 1/2 times 9.
Negative 4.
And then,
They went on 9.
right? And so which one would be a convenient one to use? Well, we probably don't want to use, those are fractions. We don't really want to use those. The one that we probably want to use would be maybe this guy right here, right?
That's what I
Because
was
we
saying.
end up with an integer,
Full number.
or whole number, right? And then there's a negative whole number, so we'll call those integers because they can be positive or negative whole numbers. So we end up with an integer change in our vertical distance for both our parent graph, and those are all integers, right? And our dilated graph, so that'd be a good one to use, okay? So if we want to graph this guy then, let's just put it in the right spot. So it's going to be -7, -8, so
So after you find all this stuff, you just have to plug it back in.
yeah, so really all we're doing, so we know here's our vertex, so we'll go back 7. So right there, and then we'll go down 8. 1, 2, 3, 4, 5, 6, 7, 8. So right there, about there. Okay, that's the point. -7, -8. Normally, I would go over 1 and up 1, over 2 and up 4, right? But what are we doing? We're going over 2 and down 2, right? So we're going to go over 2 and we're going to go down 2 to there instead,
That makes
right?
sense.
So what have we done? Well, it's going to be compressed because 1/2 is less than 1, and it's flipped because it's negative. But isn't that what we get here anyway?
Yeah.
Right, if we graph this thing, it's going like that, right? As compared to that. So it's skinnier, right? Meaning it's been compressed and it's been flipped,
Wait.
right?
Yeah.
You get the idea? Okay. Another way to maybe look at this, I know I'm showing you 19,000 ways, but I think the more ways you see it, the better you really understand it. What about something like this guy? Okay, what if we've got, let's choose the value, our parent graph is just x squared. So we're just looking at horizontal distances are just x values in this case, right? Let's pick the value of a to be 1/2. Okay, I want you to notice something then. So if we choose values in our table, when we have a horizontal distance of 1, right, what's our parent vertical distance? 1, right? If we have 2, it's 4. If we put in 3, it's 9. If we put in 4, it's 16. And there they are. There are the points. Over 1, up 1. Over 2, up 4. Over 3, up 9. Over 4, up 16, right? Well, what's the dilated distance? All we're going to do is we're just going to multiply the parent vertical distance by a. So 1 times 0.5 is 0.5. Well, look at that. Over 1, up 0.5. That's not very convenient though, right? But if we go over 2 horizontally, right? 0.5, which is a, times 4 is 2. That's pretty convenient. That guy right there, isn't it? Right? That takes us over 2 and up 2 instead of over 2 and up 4. Right? So by multiplying by 1/2, look what we did. We just sucked that point down from from a vertical distance of 4, we just squeezed it down to a vertical distance of 2. 3 wouldn't be very convenient, right? Because we get a fraction or a decimal amount. But 4 would work also, right? The parent vertical distance of 16 times a, 0.5, is 8. So we'd go over 4, and instead of going clear up to 16, we're just going to go over 4 and up 8, right? See how that a works? If we change it to, let's change it to like 4/3. Make it a weird one. So if it's 4/3, now what are going to be convenient values? If it's 4/3, let's go down to our table. Well, now that's 1.3 repeating, right? So 1's not very good and 4's not very good because 4/3 times 4 is a fraction. But 9 works great because 9 times 4/3 is 12, right? So that would be a great point for us to use. Or we'll pick a horizontal distance of 3. We go over by 3, and instead of going up 9, we're going to go up 4/3 times 9, which is 12. Okay, make sense? Okay. How about something like this? What if we want to go the opposite direction? Let's just look at a couple of these really quick. So this time we're going to try to write this in general form. But first we got to know what we have to do is we have to pick out the values of the vertex, HK, coordinates HK, and A, and then we got to write it. We're going to start off in vertex form and then just do some algebra to simplify that with order of operations. Remember what we said on Monday, I guess, right? We said that anytime you follow order of operations and you simplify a function, you always put it into its simplest form, which is general form, right? What is it for a line? Mx plus b, right? What is it for a quadratic function? Ax squared plus bx plus c. What would it be for a cubic? Well, we'll get there when we get there, but it would look just like this, only you would have an extra term out in front with an x cubed. Okay, but we'll get there later. All right, so we got to turn this into, first of all, we got to go to, what is vertex form again? A times the quantity x. If it's vertex form, we must see the vertex in there. It has to have an h and a k.
X minus h plus
There you
k.
There you go. So does that make sense that that's vertex form?
I don't know, that's what it's called.
They call it vertex form or standard form. Vertex form is a better way though, because then you
standard
can see that there's the vertex, HK, right? Okay, so we got to put it into that form first, and then from there, we can turn it into general form, right? So let's pick those points out. What are the coordinates of the vertex?
Negative
Coordinates of the
negative 1/3.
Negative
3.
So 3, negative 1. Everybody agree?
Yeah.
That's our vertex. So we know right away, we know that HK equals 3, negative 1. Now we got to find A. That's the part that I think is probably a little bit trickier, right? Well, let's think about this now. What's our horizontal distance? So we want to go over from here over to this point. That's a convenient point that I picked for you. What horizontal distance is that? We go from, if an ant's going to walk from there to there, how far is he walking horizontally?
4.
1.
Horizontally, 1, right? In the x direction, he's only walking 1. So delta x is 1. Okay, now where would our parent graph be? We go over 1, we go
Up 4.
on our parent graph. We'd up 1, right? Because our parent graph is just x squared, right? The parent graph, you get that we're always just going to compare. This one's been stretched. We're going to compare that to the shape, though, of f of x equals x squared, right? That's our parent graph, okay? So we would go over 1 and up 1 squared equals 1, right? Okay, well, what's our dilated graph? We're going over 1 and up how much? For a horizontal distance of 1, we're going a vertical distance
4.
of 4, right? So we ought to be able to find A then, right? Because we know that what A does, A multiplies the undilated value to get the dilated value, right? So 4 equals A times 1. Or another way of thinking about that is, if I just solve for A is just going to be the dilated value divided by the undilated value. Final divided by initial, right? So what is that here? 4 divided by 1 is
1.
4.
4,
Oh, God.
right? So we get 4 divided by 1, because that's what we're plugging in. This divided by that, right? Equals 4, so A is 4, right? Now we could have done the same thing. I picked a point for you, but we could have gone over 2 also, right? What if we had gone over 2? What would the parent vertical distance have been? For a horizontal shift of 2, the vertical shift would have been
5.
4.
4. 2 squared,
Oh, man.
right?
Dude,
If I'm
just don't
going
say
over
4.
2 from the origin, I'm gonna go up 4 normally, right?
I bet I can guess what the answer is.
I bet you can too. Okay,
4.
what are we doing though? So we would go over, if we went over 2, normally we would go up 4. We'd go up to there, wouldn't
Yeah,
we,
but
right?
you started at 2 this time. Oh.
See what I'm saying? So we would normally go 4, but how far did we go? We can't even see. It's off the chart, but how far up do you think we went?
16.
16. Yeah, we'd have to go clear up to 16, and that's where that point would be,
Oh, no, the answer is 16.
right? And so we're gonna end up with final, the dilated divided by the undilated, so 16 divided by 4
Oh, God.
equals 4. I'm always gonna get 4, because that's the dilation factor it's not gonna change for this graph, it's the same, right? You get the idea? So we know that we can see here that this is A, right? So this is telling us A equals 4. So now all we have to do is just the math, right? We just have to turn the function. Okay, so now we've got f of x equals A, it's in vertex form, times x minus 8, which is 3 squared, plus k. I just have to put that into general form by simplifying. Simplifying just means following order of operations, right? Okay, so inside parentheses, anything to do?
Yes.
What?
No, there's nothing.
Nothing to do there. What about exponents?
Yeah.
Yeah, there is. Exponents, I gotta deal with this stuff, right? I've got something being squared. So if we've got x minus 3 squared, how do we do that? Okay, you could just write x minus 3 times x minus 3, but let's not. Let's use our trick. Let's use a plus b squared. Let's use that pattern. You guys gotta remember this pattern. This saves you so much time. What's that pattern? If I take the quantity a plus b and I square it, what do I get? A squared
And b squared.
plus, well, at the end I get a b squared, but there's a term in the middle. 2ab, good. 2, so I get the first one squared plus 2 times the product of both of them. 2 times the first times the second plus the second one squared. So let's just follow that with our pattern. What's our a?
X.
Is x, right? What's our b?
Minus 3.
Minus 3. So then a squared becomes x squared. 2 times a times b becomes what?
2 is negative. Oh,
Not 3.
Negative 3x.
no.
2 times x
Negative
times
9.
negative 3 is what? 2 times x times
C.
negative 3.
6.
Negative 6x. Right? Does that make sense? 2 times x would be 2x times negative 3 would just be negative 6x. Right? And then plus b squared. What's negative 3 squared?
9.
There you go. Right? So there's what we get following our pattern. Okay, so then we can trade all this stuff for the quantity x squared minus 6x plus 9, but we've still got that 4 that's being multiplied by all that stuff, right? And the 1 at the end. So what's next?
You gotta.
Multiply. Good, I've got to distribute the 4, don't I?
Yep.
Right, so if we distribute the 4 all the way through, I get what?
4x squared
4x squared
minus
28. Oh,
24x plus,
36.
good, minus 1, and then the very last step.
I mean subtract.
Yeah, I'm just gonna combine those, right? Good, so I just end up then with
37.
4x squared minus 24x, what, plus 35?
yep.
That's our answer.
That was sure a lot.
It seems like a lot, but it's because we talked about it. But really, we didn't do that
Oh,
much.
yeah, you just have to do. Yeah, it's really
Right?
not.
All we gotta do is find H and K, we gotta find A. That's the part that I think you guys still are having a little trouble with, maybe, some people, right? I mean, so
I
get some
got
more
it.
practice with it. Once I find those things, then I'm just gonna do regular simplify, top-down order of operations to put it into its simplest general form. Okay? All right, so I'm gonna skip that one then. Okay, so I wanna move on and let's talk a little bit about, the 3-6 stuff. It's not hard, right? Actually, we haven't started yet. This is what we can do now, right? This is 3-5. 3-5, if you can do this, you can do all of 3-5. 3-5 is about just isolating a variable that you can point to, right? In a quadratic equation like this, because I'm able to point to a single value of x, right? I can isolate it by just reversing order of operations. And we've gone through a bunch of examples with that. I think you'll be fine with this. The tricky part, if anything, is just the 3.5 practice 2, which is simplifying radicals, but you guys know that trick now, right? So what about stuff, though? We're going to move on and look at some slightly different problems, stuff like that. Okay, this is a different kind of equation to solve, right? This is a kind of equation where now I can't point to a single x, so I've got to resort to a different strategy. So here's our strategy. Okay, I want to play a little game with you here. Okay, if you can tell me, there are 3 random numbers behind these squares, and the product of those 3 is that number. I will give you all the money in my wallet if you can predict what any one of those numbers.
4.
4. Okay, you want to play the game? 4.
Yep.
We'll try it.
Everyone knows 4 is magic
Oh,
number.
nice try.
Oh, what the-
Why didn't you ask me?
Okay, I'll ask you the next one. For a fabulous gift and prize, and/or prize. Tell me what any one of those is.
0.
Ooh, here we go, 0.
No, it was my turn.
Did you lose?
So at least one of those had to be 0. How come?
Because the product is.
Because the product is 0. So fabulous gift and prize. Reach into my drawer here. Yesterday the prize was beads. Today, ooh, this is a good one. There you go. Paper cube. I'm re-gifting a paper cube. There you go. So, so this just illustrates what we call the zero product property, right? Which just says that if the product of 2 factors or more is equal to 0, then the only way that can happen is if one of the individual factors is 0.
So
right?
it can't be a negative?
Well, these could have been negatives, sure.
No, but let's say it was negative 15 times 15.
Okay, that's going to give you a negative, very big number though, right?
Oh.
See what I'm saying? The only way you can get 0 is by multiplying by 0. That's it. There's no other way to do it, right?
Never thought of that.
So that's what we call the zero product property. And it tells us that if A times B equals 0, then what could be true? Well, either A equals 0 or B equals 0. It's the only possible way that can happen, right? So what about like this function right here then? If we've written this quadratic function, if we've already separated it into a product of factors, right? If I multiply this one out, just real quick, if I multiply this one out, what would I get? If I distribute the x, I would get,
X squared.
okay, if I distribute, let me pick a different number. So if I distribute the x there, I get x squared. What if I distribute it there?
1 X.
X. If I distribute the negative 9, I get, and if I distribute the negative 9 there, right? So this whole thing is really just equal to x squared minus 8x minus 9, right? Okay? But we want it in this form instead. It's already in factor form. If I can put it in this form where it's written as a product of factors, and I want to find the zeros of the function, well, what are the zeros of the function? Those are where the function equals 0, right? So by the zeros of the function, that just means I'm setting the function equal to 0, right? So here's the equation that I end up getting, right? I just set the function equal to 0, and what are the only possible solutions there? In order for this to equal 0, this product to equal 0, I've got this factor times this factor, right? Let's just say left factor times right factor. If the product is 0, what's the only way that can happen?
0.
Yeah, either the left factor is equal to 0 or the right factor is equal to 0, right? So either x minus 9 equals 0 or x plus 1 equals 0. So what are the values of x that make that happen? What's the value of x? Ellie, what's the value of x that's going to make that first factor 0? 9. So either x equals 9, how about this one?
-1.
-1. Those are my solutions, right? Those are the zeros,
That makes sense.
okay? What about down here? If I set this one equal to 0, I'm finding the zeros of this one. Well, 4 can never equal 0. 4 is 4. But what's going to be the value of x that's going to make this factor 0? -6. And we can do that in our head. We can just say if that equals 0, I'm just going to subtract the 6 to the other side. And I get x equals -6. Or what about this one?
X equals
1.
Those are the solutions, right? You get the idea? How about this one down here? So if this is equal, we're finding the zeros again, so we're going to set that equal to 0. There's our equation we're solving, right? Then
X has to be 0.
either x is 0 or
6.
X is 6.
x equals 6. Those are the zeros,
I knew it.
okay? So then all we have to be able to do, if we want to use this simple zero product property, all we have to do is just, we have to be able to factor stuff, right? So let's try a couple of these. So what about this one? Well, I'm going to skip forward just a little bit. Okay, what about something, I don't want those yet. Oh, I ran, no.
No
Right now?
problems.
Okay, I'll make one up. So I thought I had these set up, but I didn't. How about this? What if we have the function, what if we have the equation x squared minus x equals 6, and I want to solve that? What do you think I could do? Now let's think back to what we did back here.
Oh, I know what to do.
If I'm able to factor it and have that product of factors equal 0, I can use the zero product property, right? Okay, right now this is really tough. To find out what values of x are going to make x squared minus x equals 6, yikes, that's hard to do, right? But what if I subtract 6 from both sides so I get a 0 on the right side, okay? See what I'm saying? If I subtract 6 from both sides, I end up with x squared minus x minus 6 equals 0. Okay, that's good. Because now hopefully we can turn this into a product of factors, and then I know the solutions have to be whenever those factors equal 0. Okay, so this is what we call a quadratic equation, not a function. It's an equation because it has an equal sign in it. Quadratic equation in standard form. Right? I don't know why the book calls that other one general form. We're just going to start calling it standard form because it's so much easier to remember that way. General form and standard form mean the same thing. We have vertex form, or we've got standard form or general form. But this is an equation, not a function. When we just get everything on one side, right, and the other side is written in its simplest form, general form or standard form, and it's equal to 0, we call that a quadratic equation in standard form. Okay? So right now this is tough though. Right now, we can't look at this and say, what's the magical value of x that's going to make x squared minus x minus 6 equals 0? It's too hard. But if we can factor this, if we can break this up into a product of factors, it gets easy, right? So that's our goal. We want to make this thing look like this. We want to break this whole thing apart into a product of factors, okay? and that product of factors is gonna equal 0. Now that process, what do you think we call that? Going from here down to there. We call this process
Factoring.
factoring, yeah. Because we're breaking it apart into a product of factors. Okay, do you remember the rules for factoring? You guys did this in Algebra 1, but it's been a while. We did this as a little bit of review at the start too, right? We want this, we want to undistribute. So if you've got a quadratic equation in standard form where a, which is the coefficient of x squared, is equal to 1, these are pretty easy, right? If they factor, do you remember how this works? You know that the first terms have to be x's, because think about our pattern. If we were going to multiply this out, that would make a x, right?
Right.
And the first term of our little pattern, a squared plus 2ab plus b squared, is just a squared. Well, that gives me an x squared, doesn't it? If I have an x there and an x there, right? The question is, what's going to go there and there? Okay? All you have to be able to do is the magic numbers that we're going to pick, the magic numbers have to be able to multiply to -6, multiply to the constant, and add to the coefficient of x. So they're going to multiply to c and add to b. So can we find those numbers? That's our goal. We're going to factor this. The magic numbers have to be able to do two things. Multiply to the constant. Okay, in this case it's -6. And they have to add to b, which in this case is what? -1. So what numbers multiply to -6 and add to -1? Now let's think about this in terms of the signs. If two numbers, so here's going to be our magic numbers, right? Here are going to be the choices. So this is going to be number 1, magic number 1, and magic number 2. If they have to multiply to a negative, what does that tell you about the two signs? What kinds of numbers multiply to give you a negative?
2 and
Positive,
3.
negative.
Okay, so they're going to be opposite signs, right? Positive and a negative. If they're going to add to a negative, which one of those must have been bigger, the negative number or the positive number? The negative, right? Because like -5 plus 4 would be -1. -5 plus 3 would be -2, because most of it cancels, but there's a little extra negative, right? So let's put the bigger number first. The bigger number is going to be negative, and the smaller number is going to be positive, right? So all we've got to do then is just look at all the factors of 6, right? What are the factors of 6? We could do 6 times +1. We could do -3 times +2.
That's it.
-2.
And that's it, isn't it?
Mhm.
Because those two multiply to
What'd I
-6,
tell you?
but they add to -1, right? So there's the winner. So we end up with x minus 3 times x plus 2, right? Now we've written this in factored form, and now it's a piece of cake. What are the solutions? X minus 3 times x plus 2 equals 0 whenever, what? X equals 3, or x equals -2, right? Okay, let's try another one. Okay, try one like this. And get out your notebooks and just try this. How about if we do, whoops, how about if we do this? We're going to solve the equation x squared plus 8x equals -12. Okay, so if we're going to solve that, what's the first thing we always have to do? Right, the only way this trick is going to work is if we've got it equal to 0, right? So what's the first thing we have to do here?
Add 12.
We got to add 12. Good. So the first thing is we're going to put this into standard form. So okay, so step 1, write as quadratic equation in standard form, right? Because we're setting it equal to 0 on the right side. Okay, next step. In order for us to get this, we gotta be able to break it into a product of factors, right? It's too hard to try to just directly find the value of x here. But if we had it, if we can use the zero product property, if we can split this apart into two smaller, easier factors, right? That's good. So next step, we gotta break this apart. We have to factor it, right? So we know that we have a 1 in front of the x squared. So that tells us that the first terms of each of these factors are just x's. But now we gotta find magic numbers. Can you tell me magic numbers that multiply to positive 12 and add to 8?
6 and 2.
6 and 2.
Both of them are positive.
So we get plus 6 and plus 2. So what are our solutions then? Either x equals
Negative 6.
-6.
-6 or x equals -2, right? Okay, is this ringing a bell? Kind of?
Yeah, it sort of
Okay.
makes sense.
Okay, good.
I'm gonna be gone tomorrow.
I'm gonna be gone tomorrow, but I'll be back Friday, so we'll just kind of pick this up on
Me
Friday.
too.
I'll put an assignment up, we'll work on that tomorrow. Oh, who's gone? I forgot to take a look.
Sorry.
Everybody gone?
I'm gonna be gone.
Keely's gone?
Not today.
Today?
I'll be gone tomorrow.